Hello, everyone. My name is Garrett Mosley, and my co-author, Marianella Landy, and I are going to share some of our results from our recent paper entitled Zeros of Complex Random Polynomials Spanned by Bergman Polynomials. The results are the joint work with Kayla Johnson and Dr. Yeager, and were completed this summer as a part of a research project at the College of Coastal Georgia.
First of all, we need to decide what a random polynomial is. A random polynomial is a polynomial with random variables taken as coefficients. Now, let n sub n of s denote the numbers of zeros of the random polynomial in a set S of the complex plane. When we take the set S to be the entire plane, as the degree of the random polynomial is n, by the fundamental theorem of algebra, we know that the numbers of zeros is equal to n. To make our results non-trivial, we want to know the numbers of zeros in a proper subset of the plane. For example, when S is equal to the real line, the unit circle, or the unit disk. We note that, as the coefficient of P of n are random variables, this involves the computation of the expected numbers of zeros, which will be denoted as the boldface E on the numbers of zeros.
We will now further specify our random coefficients eta sub k to be independent and identically distributed, abbreviated as IID, complex valued standard Gaussian random variables. That is, each coefficient has mean 0 and variance equal to 1. In this setting, one of the most classical results is an explicit formula for the expected number of zeros in the set in the plane that was given by Hammersley in 1956. Later on, Arnold showed that for a disk with a radius r that is strictly less than 1, as the number of the degree of the polynomial tends towards infinity, the expected number of zeros in the disk is equal to r squared divided by 1 minus r squared, and that the expected number of zeros in the whole unit disk is n over 2. Therefore, on the average, we expect for half of the zeros to be contained in the unit disk. More recently, Ladone and his co-authors proved this scaling limit for an expanding disk that is centered at the origin.
In our project, we studied the numbers of zeros of random polynomials of the form Pn of C, where eta sub k are still IID complex valued standard Gaussian. But the spanning basis, which is the little pk here, are polynomials orthogonal on the unit disk with respect to the finite positive Borel measure mu. This means that the spanning pk's all satisfies this orthogonality relation. Here, the integral over the unit disk with respect to Lagrange area measure, and when integrating Pn times the conjugate of Pm, we have that it is equal to 1 when n is equal to m, or 0 otherwise. We remark that this relation is actually an orthonormal relation, but staying in line with the current research, we refer to it as just an orthogonality relation. In the case above, when the orthogonality relation is supported on the unit disk, the spanning functions pk are called Bergman polynomials. We say that the random polynomial is a random orthogonal polynomial when its spanning basis satisfies the orthogonality relation.
Before moving forward, let's look at some examples of these spanning Bergman polynomials. First, consider the spanning functions to be this set of pk's. In this case, the measure of orthogonality is taken to be just area measure in the plane, and we have the weight function h of z identically equal to 1. Using polar integration to complete the integral, one can show that the pk's do indeed satisfy the orthogonality relation desired. For two more exotic examples, we leave it to the audience to show that these two sets of polynomials also satisfy an orthogonality relation with the measure taken to be area measure and their corresponding weight functions as given.
Okay, now back to the full random orthogonal polynomials. On this image, we have in the color blue zeros of 4,000 different random polynomials, all with IID complex values standard Gaussian random coefficients, each of degree 25 with the monomials as the spanning basis. From Arnold's result, we know that the expected numbers of zeros in the unit disk is n by 2. The graph in the right has zeros for the same numbers of polynomials of that degree, but this time with the spanning basis to be the Bergman polynomials. From the image, it appears that there might be more zeros in the unit disk when taking the spanning basis to be this class of Bergman polynomials. But just how many do you expect?
Our first results concern the random orthogonal polynomials with the spanning basis to be taken as in the previous plot. In this setting, we were able to get an explicit and manageable formula for the expected number of zeros in the complex plane. Due to its complicated look, we have left this formula out of the presentation and will only give our main applications. First, we achieved that the expected number of zeros in a disk of radius r with r strictly less than 1 is this ratio. Here we see that there is a factor of 2 more than there are when 1 remains with a monomial basis. Next, we found such a scaling limit of an expanding disk at the origin holds, which again is more than in the monomial case. Taking t to 0 in the formula, which we note was only a heuristic, led to the conjecture that there were 2n over 3 zeros in the unit disk, which we were able to fully prove. Therefore, on the average, there are more zeros in the unit disk for our random orthogonal polynomials spanned by this class of Bergman polynomials than there are when the spanning functions are the monomials which gave n over 2.
We now seek to generalize the previous results. To do this, we need to make some assumptions on the spanning Bergman polynomials. First, we need to assume that the measure of our orthogonality is absolutely continuous with respect to the Lagrange area measure. We will also assume that the leading coefficients of the Bergman polynomials are all positive and all satisfy this root asymptote. Such an assumption at first might seem strange, but this is the classical concept that makes the measure of orthogonality to be well behaved on the unit circle and allows for the asymptotic concerning the Bergman polynomials to be established. In fact, this assumption is known as Hofmann-Stahltzotic regularity. Furthermore, under this assumption, it's known that the Bergman polynomials form bases from a large class of analytic functions in the unit disk.
Under the previously mentioned assumptions in this general setting, using classical results, we were able to retain our limiting value of the expected number of zeros in a disk of radius r with r strictly less than 1. Moreover, appealing to universality results provided by Dor and Levinsky, we are also able to prove that the expected number of zeros over the whole unit disk is asymptotic to 2/3 of n.
To finalize the presentation, we would like to thank our co-authors, the organizers of Young Mathematician Conference, and the audience for their attention. Thank you very much.